Hello everyone, for Math 1340 Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework that I've titled Chapter 3 KnewtonAlta section, Counting to Find Probability. The reason I titled it this way is because it's related to Chapter 3 material on probability. It's just that there's not a specific section in the OpenStax statistics book on counting to find probability. So what I did in your Canvas was, I gave you a link to the OpenStax pre-calculus book, section 11.7, to talk more about finding probability using permutations and combinations. So if you recall from the last video on just, principles of counting principles, right? You learned how to count with permutations, and that's when the order that things came in mattered. And you learned how to count with combinations, all right, when the order that things come in do not matter. So in this section just expands on that, and we're going to be finding probability in the usual way. Remember, the probability of an event is the number of ways that event can happen divided by the total number of possible outcomes. So we're just going to be counting how many ways can an event happen, and then we'll count how many possible outcomes are there, and then divide those for probability. So here's one of the objectives, compute probability involving permutations and combinations. So as I say every time, when you see a new objective for the first time and you're unfamiliar with it, you can move on if you want. You can try answering, but I'm going to click on more instruction. I'd recommend that. So computing probability using permutations and combinations. This is many interesting probability problems involve the use of counting principles, right, permutations and combinations. In these problems, we will use permutations and combinations to find the number of elements in events and sample spaces. Remember that probability is a measure of a particular event happening compared to all events in a sample space. When calculating probabilities involving permutations and combinations, we will do the following. Number 1, determine whether the problem involves permutations or combinations. And I kind of said that out loud a second ago. Permutations will be used when the position that things come in matters, order matters. Combinations will be used when the positions that things come in doesn't matter. Order does not matter in combinations. Then we're going to find the number of ways, count the number of ways for the event to occur. Then we're going to calculate or count the total number of possible outcomes, and then divide those, right, and write your probability as a fraction, a decimal, or percent. And they express, now this is something you've seen already, how to calculate the probability of an event, the number of ways that event can occur divided by the total number of outcomes. Now this is with permutations. They got another one later with combinations. All right, so you can read that example there. I'm just going to go to a problem and go through those steps. Right. So our question here, in a horse race with 6 horses, you make a bet by predicting the ranking of all 6 horses. If you place your bet at random, what is the probability that you will get the first and second horse correct in the correct order? Notice correct order. Correct order is mentioned. So order matters. Order matters. All right. So this is going to be a permutation problem. All right, and I'll actually pull this up on a piece of paper. Right. So it said we had 6 horses. All right, so this will be like my n, right, the lowercase n for the number of objects I have. 6 different horses. Now, what we're trying to figure out is, what's the probability of getting the first and second horse correct? Right? Picking, betting on the picking. You pick horses in the order that the 6 horses will come in. and you're calculating, they're asking for what's the probability that you choose or that you pick the first and second horses correct. All right, so order matters here, right? They even mention the word correct order in the problem, meaning that we're going to use permutations, or we're going to be counting with permutations. All right. So first, I'm going to count how many ways could I select the first and second horse in the correct order. All right. So how many ways can this event happen? All right. Well, think about it. You got these 6 spots you're filling. All right, there's 6 horses. I'm picking 6 positions. You know, from first, there's first and second to 6th place. Right. Now, if I pick, you know, horse A and horse B and I'm right, right? Suppose these are correct. That means, you know, I got those 2 right, and the other 4 don't really matter. All right, so I'm going to count how many different orders the other 4 horses can come in after me. All right, I'm going to assume, you know, I got the let's assume this event happens. Say I got the first 2 right. And then I count how many ways the other horses can come in order. Well, if I got the first 2 right, that means I picked 2 of the horses, and then you'd have 4 choices for the next horse, and then 3 choices, then 2, then 1, and you multiply those. That's 4 factorial, right? That's 4 factorial, right? Remember, permutations are just rearrangements, right? Where, again, order matters. So there are 24 different rearrangements where, you know, I get the first 2 horses correct. Say it's horse, you know, Adam and Bob, you know, and then if Adam and Bob are here, you know, there are 4 horses left. There are 4 factorial different ways to rearrange those. So there are 24. Right, 4 factorial is 4 times 3 times 2 times 1. It's 24 different ways that this event can happen. All right, that'll be the numerator of my probability. Divided by, and the question is, you know, how many total outcomes are there? How many possible outcomes are there for this horse race? Now, how many possible outcomes is now, you know, I got the 6 horses, and, you know, first place to 6th place. This is just for any possible outcome, not the specific outcomes where the first 2 horses I get correct, but any outcome. So if I choose any outcome, there are 6 horses for the first possibility, 6 possible horses in the first place, 5 in the second, 4 in the third, and 3 times 2 times 1, using that fundamental principle of counting. This is 6 factorial. Now 6 factorial is, you know, 720. 6 times 5 times 4 times 2 times 2 times 1. So 24 divided by 720 is the probability. Now I could simplify this pretty easily. Right? Probability, I said, was 4 factorial divided by 6 factorial. Well, remember, 6 factorial is just 6 times 5 times 4 factorial. Right, and then 4 factorials cancel, and I'm left with 1/30th. All right, 1 over 6 times 5. So 24 over 720 reduces to 1/30th. And they asked us to enter the answer as a simplified fraction. All right, but you see, again, I'm counting the number of ways the event in question could happen. You know, I get the first 2 horses right and rearrange the other 4, divided by the total number of possible outcomes for this horse race. All right, so back here I'm entering, again, enter your answer as a simplified fraction. Pay attention to how they want you to enter answers, right? So 1/30th. And again, they go through the explanation saying, you know, you're going to be doing rearrangements, permutations, order matters, counting the number of ways the event can happen divided by the total number of possible outcomes and simplifying. Right. Yeah, and yeah, Okay. Right, then moving on. Again, read that. Now the next one's probably going to be a combination problem since they're mentioning combinations here. You can read through the examples on your own. I'm not going to read those. Let's just get to a problem. And you've seen combinations in the previous sections video, hopefully. Combinations are used when order doesn't matter, right? Position doesn't matter. So this is a company sends 15 representatives to some industry conference. 10 of them are women, 5 are men. Only 8 representatives will be given a chance to make presentations. What is the probability that all the representatives that make the presentations will be women? All right. Now, again, it just says 8 people will give a presentation. It doesn't say that they're going to give them in any particular order. All right, so order does not matter here. All right, so again, I'll go to a piece of paper and write some of this information out. So my N here is 15. Right, there are 15 representatives. It said 10 were women, 5 were men, and we're choosing 8. Right, we're choosing 8 of these people to present. Now the question is, what's the probability that all 8 of them are women? So again, same deal. I'm going to take this event, the fact that all 8 are women, count how many ways can that happen. How many ways can this event happen? Number of ways for this event to happen where all 8 people I select are women. Well, I wouldn't. Does this make sense? That I hope. I don't know why I'm asking a question. You can't respond. I'm not going to choose from all 15 of them because there's some men in there, right? I want to make this happen. I want to make all 8 of these people that are presenting women. So that means for this, I'm selecting from just the 10 women. So this would be, I have the 10 women, and I'm choosing 8 of them. Remember this notation for combinations. Oh yeah, and an order doesn't matter, right? Order does not matter here, right? They're just being selected to present, not in any particular order. Order does not matter, meaning I'm using combinations, which I've done here. So this probability, the probability of all 8 being women, well, the numerator is going to be how many ways can they all be women. Again, I can't choose from the 15. I can't choose 8 people out of the 15 because I might choose some men. So I only choose from the 10 women. From the 10 women, I choose 8. 10, choose 8. Divided by, and then what are the total number of outcomes, the total number possible. So this is where I take any possible 8 people. So I'm choosing from everyone now, right? I have all 15 of them in my group, and I choose 8 from all 15 of them. This would be the total number of possible groups of 8 I could select. So 10 choose 8 divided by 15 choose 8. And I can pull this up, and I know that's how they have you entering it, just with the combination symbols here, but I'll pull up a calculator and we'll calculate this. All right, so in the numerator, I'll put this in parentheses. We have 10, right? The 10 women, and I'm choosing I'm only choosing from the women because I want all 8 to be women. I want this event to actually happen. So 10. I hit the math button over to PRB there, and then number 3 is N choose R combinations. 10 choose 8 in parentheses in the numerator, divided by, and then in parentheses 15 choose 8. Right, the total number of groups of 8 I could make from all 15 people. 15 choose 8. And it's very, very small, right? This probability 0.007 about, right? If I rounded to 3 decimal places, this is less than 1%, right? So if you have 15 people, 10 are women, 5 are men, and you choose 8 of them, just take a group of 8 of them, the chances that all 8 will be women is less than 1%. All right, but back here they're just having you fill in the combination stuff, right? So the numerator was, how many ways could they all be women? That was 10. I choose from just the 10 women then. 10 choose 8 divided by, and then I chose the 8. How many? What's the total number of possible combinations of 8 from all 15 people? Right, divided by 15, choose 8. Come on now. There we go. All right. Hopefully that made sense. All right, so a new question. All right, now we will calculate the actual probability that all representatives to be chosen for presentation will be women. We have found this. Express your answer as a fraction in simplest form. All right, so now let me pull that back up. And now I know it's 0.007 approximately, but let's actually write it. They want us to write it as a fraction. All right. Now you can do this a couple ways. On the calculator, I can just, once my number's up there, the 0.0069993007 like that, you can hit math, change to fraction, and it's 1 over 143. Right? It's that simple. But if you wanted to do it by hand, I'd have to use the formulas for combinations, right? Remember what 10 choose 8 means. That's 10 factorial divided by, and then 8 factorial, that was r factorial, times 10 minus 8, or 2 factorial. Right. That's 10 choose 8 in the numerator. Then 15 choose 8 in the denominator. You'd have 15 factorial divided by, and then the r, 8 factorial, and then 15 minus 8 is 7 times 7 factorial in the denominator. All right, now hopefully you can see that the 8 factorials would go away, because I can multiply the top and bottom by 8 factorial, so I can get rid of those. All right. And then 10 this up here, that's 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 factorial. The 2 factorials would go, and I'd have 10 times 9 times 8 times 7 times, well, I'll just say, yeah, I'll write it out. I don't know why I always said 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, right? And then the 2 and the 1 would go away because of this 2 factorial here. Then in the denominator, something similar. You'd have 15 times 14 times 13 times 12 times 11 times 10 times 9 times 8, and then the rest would be 7 factorial, and get rid of the 7 factorial. All right, and then you can get rid of a bunch of stuff. These both have 10, 9, 8. There's a 10, 9, 8 in the numerator, 10 factors of 10, 9, and 8 in the denominator. And then you have 7 goes into 14 twice, 6 goes into 12 twice. You have 4 is 2 times 2, so I can get rid of those 2's. 3 and 5 make 15. So I'm left with 1 in the numerator, and then 13 and 11 in the denominator. And 13 times 11 is 143, like you're seeing on my calculator. All right, so this is all equal to 1 over 143, right, if you put it as a fraction, this probability. All right, so do it by hand. I'd say just do it on the calculator and have it change it to the fraction for you. All right, so I enter the numerator here. It says see, enter a simplest form. All right, so you actually have to put it in least terms, lowest terms. Great. All right. All right, so the other objective is pretty much the same thing. It says determine which probability method for a given context. So I'm not going to go into more instruction for this because it's the same stuff. You just have to determine, would it be a permutation problem or a combination problem? All right. Now, permutation, remember, is when order matters, when the positions that things come in matter. And combinations will be used, it'll be a combination problem when the positions don't matter. when order doesn't matter. So I'll just do this one. All right. A choreographer for a musical is arranging dance moves to complement the music in a storyline. For each piece, he is arranging 5 dance moves into a routine from 17 dance moves total. So of these 17, he's picking 5 of them to put in this routine. How many different arrangements of dance steps can he make? I mean, you got the word arranging, arrangements. Order matters here. Because if he has you doing like I don't know really any dance moves, what they're called, like, if he has you doing step that, a fancy step and a plie, or I don't know, ballet moves, whatever. Say he has like, all right, say he has like a tap element and then a jazz element, right? Well, if you put the tap element first, then the jazz element second, that's totally different. That's a totally different dance than having the jazz element first, then the tap element second. Right? So the order does matter, right? The arrangement of the piece matters. So this will definitely be a permutation problem. We are listing the possibilities and order does matter. And then you have to select all that apply. So the first two are, is it a permutation problem or a combination problem? It's a permutation problem. The second two is, does the order matter or not? To solve this problem, we want to list dance moves, so order will matter, right? If you select permutation, you better select order will matter. And if you select combination, you have to select order will not matter, right? That's what it means. And so it's really up to you. You really have to pay attention, read the problem carefully. And now here, it's permutations. See the P, right? NPR. Now that we have determined the problem deals with permutations, right? They told us how many ways could he put those 5 dance moves in the routine. So remember, there were 17 to choose from, so 17, and he's picking 5 of the moves, so 17p5, right? 17p5, and I could pull a calculator up if I wanted. All right, I will. All right, remember that's I got 17 dance moves to pick from, and then PRB there, NPR 5, right? We're picking 5 of them. So there'd be 742,560 different routines this person could make. Different orders that the dance moves could come in. So 742,560 is what I'm entering there. All right, and submit. Wonderful. Continuing on, and same objective here. Oh, no, it switched back. But it's still the same thing, really. Still the same kind of issue where you're starting off, what kind of problem is it? Permutation, combination, order mattering, order not mattering. So a swimming team from East High School is participating in a swim meet with 3 swimmers competing in the butterfly stroke race. There are 15 total swimmers competing in the butterfly stroke race. What is the probability that 2 East High School swimmers finish first and second in the race? And it says enter your answer as a simplified fraction. All right. Now, all that matters here is that 2 people from this school finish first and second. Right? It doesn't say really specifically that this person has to finish first and this person has to finish second. Right? So think about it. Say Bob and Tom are from East High School. If Bob finishes first and Tom finishes second, that's 2 East High School swimmers finishing first and second. But if you switch it up, if Tom finishes first and Bob finishes second, that's still 2 East High School swimmers finishing first and second. So the order that these, the order doesn't matter here. Right? As long as these 2 kids are finishing first and second, it doesn't matter if one's in first or the other's in second or whatever. As long as they're finishing in first and second, this event is satisfied. All right? So All right, so I'm going to paper here. It said there were 15 total swimmers. Right, 15 swimmers. 3 of them are from this East High School. All right, 3 of the 15 are from this East High School. And let me get rid of the calculator here for a second. We're asked to find what's the probability that two of these three finish first and second. 2 from East High School. I'll say 2 from East High finish first and second. All right, so let's look at this event. Now, how many ways can this happen? All right. So what I'm going to do is count, how many ways can 2 of these, I'm only really focusing on the East High students at the moment. All right, how many ways can 2 of the East High students finish first or second? So there are 3 First I students, and I'm just going to choose 2 of them to finish first or second, right? Because again, it doesn't matter if, like I said, Bob finishes first, Tom finishes second, or if Tom finishes first and Bob finishes second, as long as they're from East High, right? So that's why I'm using combinations here, right? All right, but that's just picking the first 2 places, though. All right, that's just picking the first 2 places, and then you got to use. I'm going to use my fundamental principle of counting, and the next event is just the rest of them, the rest of the race. All right. So if I pick 2 people already, and there are 15 swimmers, that means there's 13 left. So there are 13. The first and second place are determined already. Right, there are 2 from this East High, and then there's 13 left. Now, how many different ways can they come in? Remember, that's 13 factorial, right? Because I picked 2 of these people to go in the first and second place, and then the remaining 13 swimmers can go in any rearrangement, right? This just takes care of all the rearrangements of those other 13 swimmers. So that's going to be in the numerator. 3 choose 2 times 13 factorial. All right. Again, picking 2 people from East High to finish first and second, and then rearrange the rest of the 13 swimmers after I pick 2 of them. All right. Then the denominator is the number of total possible outcomes. All right, now it's a race. Right. There are 15 swimmers in this race, so the number of different outcomes is 15 factorial. Right. The number of different, I guess order would matter in that case, but the order that the first 2 kids come in doesn't matter. That's why I used combinations there. And I'm rearranging the orders, doing a rearrangement for the rest of them, so order is mattering. And then so the total number of outcomes for the whole race is 15 factorial, right? And then this can be simplified pretty easily. 3 choose 2. If you do 3 choose 2, that's 3. Right? It would be 3 factorial divided by 2 factorial times 1 factorial, or just 6 divided by 2. All right, 3. And then you have 13 factorial here, and then 15 factorial is 15 times 14 times 13 factorial. And 13 factorial would go away. 3 goes into 15 5 times, so I have here 1 out of, and then 5 times 14 left in the denominator, which is 70. All right, so the probability that both the first and second place finishers are from East High School is 1 out of 70. All right, it says enter my answer as a simplified fraction. But wait a minute. Before I enter that, actually, all right, I probably should have thought about this as if it were a race. All right, so it is a race. It's like, all right, if I think about this, so you got, say Bob and Tom are from East High, I'll say BT, and then you have the other 13 kids, right, the other 13 swimmers. Uh, okay, order, all right, I apologize. This would be a totally separate ending, wouldn't it? Tom and Bob. I know I was saying that earlier, but this would be a separate race. So this should actually be 3p2. Yeah, that should be. Yeah, that should be 3p2. I am very sorry. Order does matter here. In thinking about it some more, order matters because again, this is a totally different outcome than this. Right? It's a totally different race. I guess that's a good thing to assume. You know, if you're talking about a race, order matters, right? They mentioned a first place and a second place. So yeah, sorry about that. That should be a 3p2, which would change this to 3p2. And then this would be not, this wouldn't be, all right, I'm sorry, back it up. Oh, that would just multiply that top by 2, so I'd have 2/70ths. This would be 6 instead of 3, which is just multiplying 3 by 2. So 2/70ths or 1/35th. All right, 1/35th. So the probability would actually be 1/35th. Again, I apologize. Please understand. Just, it's a race. Okay, I probably should have just thought that in the beginning. It's a race, or order. Typically in a race, you know, the order people come in matters. All right, so let's go back to the website. All right, sorry, I entered the 1/35th there. Right. Yeah, see, it's 6 times 13 factorial. Yeah, 3 times 2. They'll say 3 choices for a swimmer from East, then times 2. That's the same as 3p2 right there. Yeah, so 6 times 13 factorial divided by 15 factorial, 1/35th. All right, so I guess you could take that away from that problem. If it's a race, you're probably using permutations, right? Order matters. All right, okay, that gives rid of that one. And then again, we have this, just again, figuring out which method to use. Does the order matter or not? Patients in a clinical trial are taking 9 medications. Doctors want to test to see whether administering 2 specific medications before the other drugs affects the patient's symptoms. How many ways can the doctors give patients 2 medications before the other drugs? Well, So it doesn't matter what order the medications come in. Maybe it would, you know, because side effects or something. But if you're giving them 2 medications before the other drugs, 2 specific medications. So, all right, I'm gonna say that if you give these people 2 medications, you know, before these other drugs, and then see how they're affected, I would say it wouldn't matter, you know, because you're giving them, like, say you give them drug A and drug B. Well, if you give them drug A and drug B and then the other meds, or drug B then drug A and then the other meds, you're still giving them these 2 drugs before the other drugs. But then again, because of possible side effects, maybe it would matter which order the drugs came in. All right. So I would argue that it was a combination problem, because but then again, it might matter. All right. I can see an argument for both. That is unfortunate about this one. So I'm going to see what they say. Permutation. So looks like because of side effects, it matters what drug comes when. All right, so that makes sense after seeing it, of course. But, if I give the person drug A, then drug B, and then these other drugs, versus if I give them drug B, then drug A, and then these other drugs, perhaps the different order that the drugs I gave them will have an effect on how the other drugs will be affected, how the other drugs will affect them. So permutation, order will matter, or the order of the drugs will matter. Again, which would make sense when you're talking about side effects, right? Kind of like a race earlier, right? When you're talking about race, order matters. The order that you take certain drugs in because of side effects that could possibly arise would matter. All right, I can see that. So hopefully that was clear. I apologize for the vagueness of this. Right? It's sometimes it can be a little unclear. Now they're asking for the number. How many? Now that we have determined the problem deals with permutations, calculate the number of ways that the two medications can be chosen from 9. So again, they have the 9 medications. They're picking 2 of them in a particular, not 92. 9 pick 2, or just 9 times 8, right? You have 9 for the first drug, choices for the first drug times, and then you'd have 8 choices for the second drug. 9 times 8, 72 possible ways you can submit those 2 drugs in different orders. Okay. All right, and that looks like it for that. All right, so again, a little tricky. Some of those, does the order matter? Does the order not matter? See, even I had a problem determining. So I'll say this much: if it's a race, order matters. Right, position matters when counting. And I guess if it's drugs, right, if you're talking about what order you should take certain drugs in, because of the possible side effects one could have before you take another one, or interactions they could have, order would matter there too. All right, but if you're just selecting a team, like if you're or a group, like that one with the groups for presentations, and not mentioning what order they need to present in and stuff like that. If the word arrangement isn't in there, if the word order isn't in there, then order probably doesn't matter. If then you're going to be using combinations. All right. So hopefully watching this is a kind of is an okay guide for you while you work through this assignment on your own. And let me know if you have any questions, of course, throughout the week or whenever you take this. And thank you very much for watching.